that we can identify for control systems, and also address already what we can use them for. So we start with stability, which is the central property of any control system. It's the minimum requirement that we always have to satisfy that we stabilize a system. And we have seen that one strategy to stabilize could be a replacement controller in the case that the system is controllable. Controllability, thus, is another very important property. This is the capability to steer a system to any point in the state space that we want. If that is the case, then we can use a simple static feedback law in order to stabilize the equilibrium point, that is the zero at rest condition of any LTI system. Okay? Using a state feedback as point placement controller, however, is practically not an option because we can only make use of the output, not of the state itself. The output is typically a subset of the states, and thus, if we want to make use of any theory that uses state information for control purposes, we have to somehow reconstruct the state from our current output. And this property is called observability. If we can, from a measured output, reconstruct the exact state the system is in, then we have the option to set up a output feedback dynamic controller, which then uses the placement for the reconstructed state and is implemented. Okay, so therefore, controllability is the property that we need in order to construct a pole placement controller. Observability is the property that we can make use of in order to implement such a pole placement controller. And that's basically where we stopped. We know now how we can design a pole placement as state feedback. We know how we can construct an observer as a state reconstructor. Today we will see how we combine the two in order to realize a compensator scheme. Okay? Before we do that, I want to conclude my remarks about duality and Kalman decompositions. So basically making connections between controllability and observability regarding the matrices. We have seen that for any dynamic system I can find a dual system where basically also the properties controllability and observability change roles. And that is also one of the reasons why we can use the very same command in MATLAB to basically construct a pole placement controller and a neutral observer. So if you use duality, then this is in fact the same type of computation. I started last time with Kalman decomposition. I will probably repeat this in the first maybe 15-20 minutes so that it is not, we must talk about this in a rush. So let's go through these slides starting from here again and then finish off this chapter. After that will be disciplinary onwards. So if we have our state space representation, then we know that there exists a state transformation which can bring the system into a specific form, for example in the controllability canonical form, in the observability controllability form, and so on. We have identified 4 canonical forms. Now suppose we can find a transformation that brings the system into this type of form, where we have basically a state decoupling, where we have one part of the state space Z1, which is influenced by the input, and an autonomous part Z2. This, of course, exists, I mean, you could say exists in general, if we assume that this Z2 could be an empty state. If we assume that this A22 or the corresponding Z2 is not empty, then this only exists if the system is not controllable. Okay? Right? But so let's assume the system is not controllable. So A, B not fully controllable. If that's the case, then such a transformation exists, which basically yields a decoupled there exists a decoupled subset of the state space, which is purely autonomous. So this is autonomous as a dynamic or a subdynamic of the state space. So which means that this part of the state cannot be influenced by the input, which also means that we have no chance of controlling it. We know that the solution of this part, that the Z2 of t then follows which dynamic. So if I compute the Z2 of t, that would be what? How can we explicitly compute the state trajectory of this substate Z2? According to our general formula, what's the solution for this part of the state space? It's autonomous, not affected by the input, so it's a simple dynamics. What do we obtain if we solve that? What's the solution for this part of the trajectories?
It's e to the power of a times t.
Exactly. So a e to the power, so the matrix exponential a to 2 times t times the initial condition, I maybe call this the Z2 of 0. Okay, so it's the autonomous dynamics, this is how it works. And we know already that two things can happen. These dynamics can be asymptotically stable, which means that the eigenvalues of a to 2 then all lie in the left half plane. However, if there is one eigenvalue which is in the right half plane, then we have what we call uncontrollable and unstable modes. They cannot be stabilized by the system. Okay? So since this is autonomous, since this part is autonomous, the eigenvalues, they are basically the uncontrollable modes of the system corresponding to the Z2, and there is the concept of stabilizability. Stabilizability. And that would be uncontrollable modes have to be asymptotically stable. If that's the case, then I can still stabilize the overall system, even if modes of Z1 are unstable. Then I can stabilize them using a partial state feedback if you want. But if Z2 contains unstable modes, then we have no chance of stabilizing the system. So stabilizability is a weaker condition than controllability. We need not be able to fully control the state, drive it to 0, because some modes already go to 0, and these are the uncontrollable modes. Okay? We have also seen that this basically gives rise also to something which is an alternative test for controllability, the Hautus test, which basically states a system is controllable if and only if the rank of lambda I minus a b is n, so it is full rank, if you want, full row rank, independent of the lambda. So there is no, if you want, eigenvalue of a for which the rank drops. That's basically the condition. Just a quick check why this is equivalent to controllability. So basically, a short, maybe sketch, I'm not doing it in detail, of the proof of the Hautus test. So we have the first direction. I abbreviate this with this symbol. So I assume the system is controllable, then follows that the rank has to be full. And the proof idea of this would be a proof by contradiction. So assume that a b is not controllable. If it is not controllable, then there exists a transformation which basically brings the system into this form, where the A22 is not a zero matrix, right? So this is possible. Then exactly we can find an autonomous part of the state space, right, which we cannot influence. Then there exists a transformation T such that we have the system dynamics such that I call this star holds, okay, so that we can bring the system into this form. And now we basically have to prove that then for eigenvalues of A, for certain eigenvalues, then the rank will drop. We can do this by constructing an eigenvector. If we multiply an eigenvector to this, so for some lambdas for which this eigenvalue basically makes this 0, then this also has to become 0. Then we have shown that this works. So then construct or take a left eigenvector of A, I call this V of A, such that then A times, and V of course is then unequal, is not equal to 0. AB equals lambda V. Okay, so that's the case. And then we basically construct an we construct a vector which we can multiply from the left to this whole thing. So the first part of this vector is V and the second part is 0. So if we do that, then basically the rank drops for the whole thing, as we will see. And basically this should be an eigenvalue of A to 2. Sorry, so the eigenvalue of this A to 2. Okay. So then, then what we would have is if we multiplied this whole thing, so take that value, for a W, which is basically a 0, V, and sorry, I wanted this, it can be a left eigenvalue, it can be a right eigenvalue, whatever, I'll do 0, V, and basically, let's use it as a left eigenvalue. So let's do this. I'll make this a left eigenvalue, dt equals lambda v. So I make this a left eigenvector. Set that, so it should be from the left. This. Okay. Then for this part, so then we have the v. Let's make it all transpose so that it is filled in notation, dt, times our transform A, A11, and then minus lambda I, 0, and A12, A22 minus lambda I, and then I have basically the V1, 0. This here would be a vector, okay, so this so that it's clear that this is a row vector of zeros. So if I multiply this from the left, this basically means that I get nothing here because this has a 0 this time. Here I get basically my eigenvalue condition, which basically means that this becomes 0 and this is also 0, right? So this is basically a 0, 0. This becomes a 0. So if I multiply this here, and write it in this notation, and what I basically get is a 0, 0, I get 0, 0, 0, 0, so everything 0, and this basically means that I have got rank because I can find a vector that is in the kernel of this whole thing. Right? So if I multiply it, this becomes 0. This vector is not a 0 vector, and therefore the rank of this cannot be full. Right? So from this follows that the rank A minus lambda I, comma B must be less than, right? Because this was, because V is basically V, and Russell transpose, which would be a vector 0 and V. And this is not a 0 vector, so this is not a 0 vector. This is in kernel element, kernel A minus I, V. Okay? Thus, we have a contradiction. So we have assumed the system is not controllable. We can bring it into the specific form that we have seen there by means of transformation. Then we can construct a vector which is basically in the kernel of this thing, which is not a 0 vector, therefore the rank cannot be n. Okay, so this is one direction, so that we've seen that. And the second direction works on a similar principle. That's why I've introduced it here. We basically make use of this specific form. So if we have this form and you compute the controllability matrix, we will see that this has not full rank. Okay? So the way back follows the same principle. So basically assume that there exists a vector. There exists a vector V, which is not 0. And the undefined 0 vector, which such that we have a basically V transpose A. So again, a left eigenvector equals lambda V transpose. And Vt B equals 0. Okay, so this would mean basically start with the assumption that this does not hold. Okay, so the rank is smaller than, thus I can find such a vector. Then the controllability matrix. And again, I can bring the system into the controllability form. And then again, if I compute V transpose times PC, the controllability matrix, this would be then basically dt times, and then we have B, AB, and so on, n minus 1b. What we obtain here is basically V times B is 0. This is any V transpose times some power of A gives me a lambda V. So I basically get 0 here everywhere because this is 0. This would be lambda times 0. And then I would get lambda, so I basically get lambda squared 0 until lambda n minus 1 times 0. Right? So everything 0. And thus, the rank of this controllability matrix is not full. Thus, rank PC smaller than n, because again, I found a vector which is basically in the kernel of this, and I cannot have full that would be just a sketch of the proof why this Halkus test is equivalent formulation for controllability and equivalent check as the Kalman, or the rank condition of the Kalman controllability matrix. And it basically uses this transformation where you can see the outcomes. Okay? All right so far? Or any questions? Then we can do something similar for observability. Again, if the system is then, we have the given in the state for representation, and we say that the pair ACT is not observable, then there exists a transformation which brings the system into this form, where we can basically see that the second part of these dynamics, the Z4, is not visible in the output, right? It's only visible in, only the Z3 can be seen in the output as some subset, but the Z3 is something which is unaffected by Z4. Therefore, we cannot reconstruct Z4 from the output measurement. So this means it's not observable. Again, we can find something which is similar, namely, or find a similar terminology, that the eigenvalues of A to 2, they are called the unobservable modes. Okay? And we have something similar as stabilizability, which we then call detectability. And detectability would mean that the part of the states that we do not observe, they should at least be stable, because we cannot see if this blows up. Right? It cannot be seen from the output, but we want to make sure that this part is stable so that we don't have internal states that basically blow up while we do not see them. So detectability would mean the unobservable modes are asymptotically stable. So I can basically I can reconstruct all the unstable modes if necessary, right? I can do that at least, and then see if the system goes wrong. And again, I can find so this should be observability, of course. Observability and similar test, similar Halkus test also exists then for observability. We basically have rank condition lambda I minus A and the CT, which means we do not have, for us, so we should observe it also. Observable. If the system is observable, then there is no eigenvalue or no lambda such that this thing drops rank. Okay? I'm not going to go through the same similar type of proof, but this is the, let's say, complementary part for observability. Okay? And now we can put both things together. So we can find a transformation for a system that is neither observable nor controllable, which basically yields this result here. Okay, so this system A, B not controllable, A, C, T not observable. Then I can find this partitioning. If it is, for example, controllable, then this partitioning would yield zero matrices, and zero units. And in fact, how this would look like, we can basically also illustrate using a signal flow graph. Maybe that's the easiest way to illustrate how it works, so that we can really see from the signal flow what's going on. So what you can see is that the input only affects x1 and x2, right? So the rest is not affected, and in fact the x3, x4 is again autonomous, right? So you could do a partition in this form to see that. So if I partitioned it in this fashion, then you would see that this looks exactly like what we've seen 2 slides before. Okay? So again, the part 3 and 4 is autonomous, and it is not affected by the input, so this is not controlled. Okay? But moreover, we also are interested in basically the lower part, the output part here, and there we see that that the x2 part is not seen in the output. So there is the following picture. We have our input, U, which, yes. So this via the V1 goes into or affects the state x1 dot, which after integration comes to x1. This will be fed back via the A11 and via the Z1. Probably should put a transpose here, but never mind. So this goes to the output Y. So that's the part of x1. We can see that this is affected by the input. So if the A11 is controllable, then we could control the full thing. And it is also seen in the output, so it should be observable. Now, the part 2 also takes the input. This goes into the x2 dot, which after integration comes to x2. But x2 is not fed forward to the output, right? It's not seen in the output. What is the case is that the A11, the affected A12, comes in here. But it doesn't go anywhere. Put it in the feedback, I can do this like that. A22 comes back here. So that's what we have. Now, this is controllable, but we do see the output, so it's not observable. Now we have an x3, which after integration, that x3 which after integration becomes an x3. We need the A33 for this to be completed. We add the A4 in there, but we do not see this in the output either. So the only thing that happens here is that this guy, the x3, this goes with the A23 goes in here. But this is neither affected by the input, nor is it seen anywhere in the output, right? So it's not observable, it's not controllable. And then finally we have an x4 dot, which integration coming to x4. This is seen in the output, right? So here, this goes as one component into the output, so this should be observable, not controllable because the input does not affect it. A4, basically like this, and this goes into 1 and 3, so this here, A3, 4, this goes in here, and A14, this goes in here. Okay? So, in a sense, this one here is, this part is controllable and observable. The red part is controllable, but not observable. The green part is nothing, right? Neither observable nor controllable, and the orange part is observable. I'm not writing not part in here, it's on the previous slide, but that's there, I think, from a graphical description of a signal flow graph, you can directly see why this is the case. You can, of course, also put up the controllability matrices and observability matrices, and you will see a similar effect. But that's basically graphical verification of what's going on with this partition state space. I think last time I showed you at the end a numerical example where you can see how this looks or could look like. We need, of course, at least a 4-dimensional state space so that we can neatly partition it like that. And there is also a constructed way of setting up this transformation, right? So this T1, T2, T3, T4 can be constructed from the known controllability and observability properties. Okay? So that's something that we can do. And this is the final Kalman decomposition, which basically shows all the workings of these two properties. Okay. Any questions, remarks here? Yes?
Why is the A14 not going to the blue part of the signal flow diagram?
Oh, yes, sorry, it's the 1-4, yeah. The 1-4, and I probably missed another one, right? So there is the A14, yes, it has to, it's called 1-4, so I have to put it here. Thanks for pointing this out. It goes here. And thus, these two, they affect the output, yes. Thank you. And we have, let me check, we have an A2-4 also, so I have the 3-4, so this one, A2-4. This is needed, so this is just a point. And we have the A2-4. A2-4, which goes here. Yes. So 3 is 3, 4, like this. And that is basically, in fact, this is again, the A4, the X4 is completely autonomous. X4 not is only dependent on X4, but it is seen in the and similarly, the X1 part has two parts basically of its solution, one concerning the X1, one concerning the X4. X4 is autonomous, and therefore no other part of the space is visible. Thanks for pointing this out. Any more questions here? Yes?
Is there like a practical reason why we do this Kalman decomposition with the transformation and so on? Because I just can look at the controllability and observability matrix to determine if it's observable or controllable.
Exactly. So what this allows us is to identify the modes. Okay? So a mode which is controllable but not observable and so on. I can identify the parts of the state space which belong to which or which have which property. Okay? So these can be associated with actual modes in the system. Right?
And modes is, so what are modes?
Modes of the system would be, so how could I best describe this? Maybe if you think of a mechanical system, maybe a spring mass damper system. So you have basically one part which deals with the velocity component, one with the positional components. And so you could identify one as the positional mode and one other as the velocity mode, if you want. Okay? And thus you could now say one may be controllable, one might not be controllable. Okay? So if you want physical interpretations, you can sometimes, of course, make this physical analogy that you say my x1 in this case corresponds to, I don't know, the voltage in across a capacitor in an RLC circuit. Okay, but that would be the physical connection. And if you say that x1 is neither controllable nor observable, this would mean you cannot do anything about this voltage. Okay, so
it's like more for system understanding.
It's in a way, well, a more in detail analysis of what's going on. Okay? If you want to design a controller, you do not necessarily have to perform such a transformation, right? But it gives you a little bit of extra physical intuition of what's going on. Okay. Question last time was if we have, or we have so far seen in our example of the RLC circuit, something that was both controllable and observable. Practical example of something which is observable or which is not controllable or not observable. Any ideas of a system which would be observable, not observable and not controllable? How can you, what type of a system would that be? Can you think of, or did you maybe come up with anything that where you see what this means? Example of a non-controllable system.
Pendulum?
Sorry?
Pendulum?
The pendulum? You mean our inverted pendulum? Well, then it would depend on what would be the actuator, or is there no actuator? If there's no actuator, no input, of course it's not controllable. Okay? But what I want is an example which does have an input, okay, some actuator, but nevertheless is not fully controllable. Of course, some parts of the system will be controllable, but it is not fully controllable. So if I think of a pendulum on a card, okay, and I have, I don't know, this pivot here. If I have something like this, and now I could have as an input, for example, a force on this card, okay? That's, by the way, one of the mini projects or projects that we have for you. Now, you could say, I want to use that force in order to basically set a certain, I don't know, position of the card and position of the pendulum. So, in that case, it is possible, by just actuating the card, to basically manipulate the pendulum. You can swing it up and you can stabilize it, all of that. So that would be controllable. Okay? So what is if I have two of these, but I have just one actuator? Then it's probably not controllable, right? So I cannot swing up. So if they are not in the same initial condition, then I have no chance of basically swinging them up both, right? I will only be able to swing up one, but the other not. Or if I have one up, then the next one then will be destabilized. So I cannot basically set a position for both of them and just have one actuator if they're not in the same initial configuration. So that would be one example. And similarly, of course, if I just measure this angle, I would have no chance of determining this angle. And even if I add, for example, the position here, it doesn't matter. If I have the x, I still do not know what about the pendulum angle here. It's maybe a bit of a pathological example, but that just practically shows if I have just this input, I can only control one of these pendula, not both. And if I measure just one of the pendulum angles, then I cannot observe the full state of such a system. Okay? First, then you can ask, what about a double pendulum? Something like this. Okay, maybe again on a card. If I again have this just by intuition, fully controllable or not. Can I swing this up, basically? Yes, you can swing it up. Can swing it up. In this case, it's possible. You can even add a third one and you can still swing it up. Okay? It's harder, right? But you can still do that. Okay? Because in this case, basically, they are affected by each other, and I have to, of course, if I want to do this, I have to measure more angles. But also in reality, of course, you can also ask the question, what's the minimum set of sensors which I need in order to basically control or at least observe the system, right? That's, of course, a question of how expensive you have to design your system. And of course, nowadays, there's a desire to reduce the number of sensors, if you can. And if you can use filters or reconstructors, Nuremberg observers, then that would be in software typically cheaper than if you spend on sensor hardware, and maybe even more exact. Okay? So that is a last remark about controllability and observability. Unless you still have questions about this. Okay, so then let's finish this chapter with the topic of dissipativity. And that's basically something which adds both in terms of our physical intuition, and it also extends, if you want, the outcome of argument to open systems. So, if you remember, the outcome of stability asks the question of when is a system stable, and this was also always addressed for the autonomous part of the system dynamics. And that is also, if you think back to your bachelor courses, this is typically the argument that we make. We look at the eigenvalues of the system, and there is no influence of the input. So autonomy, autonomous systems, that's enough for us, and has been enough for us for as long as we've discussed these subjects, in order to reason about stability. What now if we are discussing interconnected systems? And that is one of the main arguments that I want to make throughout this course. And that is also why this Hamiltonian framework is so important. If you look at current engineering problems, then typically these are complex systems, right? So they are certainly consist of many subsystems, all of which are interconnected. Now, we need properties and we need mechanisms to reason about the complete system dynamics while basically decomposing this into smaller subsystems and maybe inferring from properties of these subsystems what the overall system does. Okay? So that's a very important thing in modern engineering, because our systems get more and more complex, certainly complex. And therefore, dissipativity or passivity, we will see the difference soon, is something which is very important. And secondly, it has a very nice energy interpretation as well. It's basically something that you probably have an intuitive understanding of what dissipativity means, and it's very closely related, just cast in a mathematically rigorous way. You can see that this is roughly 50 years old, and was introduced by Jan Willems as a concept, and has proven very, very important throughout. So the main thing is, this is kind of, and I put this into inverted commas, this is kind of a stability theory for open systems. By open, I mean systems that can be interconnected, so that have basically inputs and outputs, and that's what we always have. You could say that this is an U and a Y, or you could say it's an E and an effort and a flow in the Porte-Hamiltonian framework. There we do not distinguish which one is the input, which one is an output, a priori. Of course, by the problem setting we know that, but in principle we have both, because we interconnect and they exchange energy, or we identify this in the classical state-space formulation with the U and the Y. So this is basically what we can do here. So we can reason about passivity for open systems, and by this I mean systems with inputs and outputs. Inputs and outputs, this would be a U and a Y, or systems that are interconnected by Dirac structures, right? Or I can say ports, right? Systems with inputs and outputs or ports, okay? And this concept was first introduced for the general nonlinear state space form. I'll just repeat that. That was the x dot equals the f of x and u. I leave this in the CISO form, but again, you can basically cast this in a you can cast that h more typical term h. I can cast that in this form. So this would be a nonlinear CISO system. For these systems, this has been introduced. In our linear case, that would be x dot equals ax plus du, and y equals ct. X du is of course also possible, but again, I drop this for simplicity, but it all holds for the general case as well. Okay? Now, what does dissipativity mean? The mathematical definition is given here, but I try to recast this in a more intuitive fashion. If we look at such a system, whether it's the general nonlinear type or the special case of a linear system, we have basically two things if we talk about these systems in possible interconnections. One is called a storage function. Storage function we can think of as basically the stored energy in the system. Okay? That's the storage function. And then I have the interconnection with the environment, which is some function of the inputs and outputs, and I call this the supply rate. So, if you connect your RLC circuit with a battery, for example, or you connect your, I don't know, inverted pendulum with some actuator which puts in energy. Okay? We have to look at these two things, and dissipativity only says, if I look at the storage state at the initial situation, at some x of t, initial state of my system, and I compare the storage state to some storage state in the future, so some capital at some capital t in t seconds, then the stored energy then will always be less or equal to whatever I have supplied to the system. And supply in this case, the supply rate, supply is, if you want, it's a power supply, so W of U and Y is a power. I integrate this over time, I get energy. This can be seen both as energy provision, so I put in energy into the system, as well as energy extraction. Basically, we just look at what is the net of this integral, right? So I have positive power, negative power, I integrate over it, and this will at most be the storage state of my future time, of any future time, basically subjected or on top of what I have now. Okay, so which means the system cannot generate energy on its own. You could say that this is something very, very basic. That's probably something that is known in physics. There is no mobility. I cannot generate energy in the system. I always have to provide it externally. But you will see that this framework, which specifies this in a mathematically rigorous way, is very beneficial and helps us also to reason about stability of interconnected systems. But so the basic idea is something very intuitive, I guess, physically, it's a physical knowledge. You cannot generate energy on its own. You always have to basically consider the external energy, the supply that we have. Okay? Got clear or not? So, formally, you have a supply rate. You can identify this W with a power, right? A power port, if you want. We integrate this over time, and this should not be infinitely large, right? That again is something that we have in reality. We will not be able to have an infinite source of energy. Now we have the storage function. Okay, the storage function B. You could say that this is basically the energy storage. You could identify this with the energy storage. Of course, if you have some non-physically motivated state X, right, a state transformation X, which is not physically motivated, you will still be able to find a storage function V, which then is not directly linked to energy. But what I'm doing is I'm saying you can, if you have a physically motivated X, like we basically derived it in our Ford-Hamiltonian framework, then you can associate the corresponding storage function with the energy function. Okay? But this is not a necessity that this is an energy function, otherwise it would have been called like that, but we call it a general storage function. Okay? It stores quantities, but you can interpret this as energy storage. And then in the integral version, this means, so this would be kind of the energy storage at time t. So if you want at the start, this is the energy storage, the storage level, if you want, after time t, after the system has evolved, and that's the supplied energy, where, as I mentioned, supply is interpreted as both provision of energy and extraction of energy, so it's the net supply, if you want, net supply. Now, so this would be the general dissipativity property. This would be dissipativity, and in the case that we have a special supply rate, namely the power product, if you want, the duality product of input and output, then this is called passive. Okay, so this is just a subcase of dissipativity where the supply rate takes this particular form. And if you look into the literature, you will also find something which is called a strictly input and strictly output passivity, where you then basically have something which is just a product of the inputs, a product of the outputs. So there are different versions, but for us, typically, this passivity definition is left. And this here, this is called dissipation inequality. Okay? Dissipation inequality. If this holds with equality, we call the system conservative. Right? That's also, I guess, something that we've heard before. A system that does not dissipate energy is called conservative. But in general, real-life systems would be dissipative, where this is an actual less. Okay. So that's the concept. And now we'll see a little bit how we can make use of that and how this is related to stability. That's the only thing that I will address here at this point. But let's go through it step by step. What we can also do is, if this V is a function which is differentiable, and if you think of our Hamiltonians as energy functions, they of course are differentiable. But especially in the nonlinear case, we can find cases where it is not differentiable, at least not in all points. Then a differential version of this holds. Basically, if you look at this, a differential version would mean I take the V dot of x, so basically the dV dx x dot, okay? And if I do this formally, then basically I should say this is then a. So typically the dV dx would mean a gradient, which would be a column vector. This formally has to be a row vector. Now what would this be? Or this should be then less or equal than W of U and Y. So this would be the differential dissipation inequality. So if you look at the red one, dissipation inequality, I basically take the time derivative of this, I get this expression. So instead of having the energy supply, I now have the power, and this is equivalent to the rate of change of our storage. How does the energy, stored energy, evolve over time? Well, it is always less or equal than the supply power. And that's what it says. Okay? Now, this can be recast in equivalently into two, basically, or if you want, a set of equalities. Basically, if I look at this, that's one slide. So, the differential dissipation inequality. And now I take the example that it holds in general. Let's take the passive case. Then this would mean that I have a d dot of x, which would be dv dx transpose x dot. This would be the dv dx dx transpose times the passive case, and I also make it the input affine case, so that we have affine. Then I say this is an f of x plus a g of x times u. Okay? And this would be less or equal than my y transpose. Make it CISO y transpose u, which would be an h of x times u. So this would mean we have the x dot equals an f of x plus g of x times u, and y equals an h of x. So that would be, for example, the inverted pendulum as we derived it also in class. This would be the input affine case. CISO, so u and y, MIMO would work, of course, as well. And I have also the non-feed-through term here, but it would also work. So if this is the case that we have, then basically we can recast that as something like the dv, sorry, probably should write this as a proper gradient, dv dt f of x. Less or equal than u, and the dv dx g, suppose g of x times u equals the h of x times u. Basically, sorry, this should be h transpose u. Why? Because if you go backward, if you add these two up, certainly this comes up. And the way back, you can also argue that from there, just by comparing these parts, right? So we have basically something which involves the input u, right? And this would be this part. And we have something which does not involve the input. It's kind of the drift, this one. And therefore, these two conditions, also called the Hill-Euler conditions, this is an equivalent formulation of the differential dissipation inequality. So this can be alternatively derived, and in the linear case, this is in particular nice. So now the linear case. So if I again look at my xt equals ax plus bu and y equals c transpose x, then quadratic storage function. Take v of x to be some quadratic storage function, xt qx, where q is positive, semi-definite, and also symmetric. So this would be quadratic storage function with positive, definite, symmetric Q. Now, the question is, of course, that this always exist. If we look at our Hamiltonian modeling, then we would always end up at something which is at least positive semi-definite symmetry. And to make this positive definite, we typically just have to add something on top of it. But in most cases, we will find this to be the Hamiltonian, and therefore this would work directly. So if I again look, let's abbreviate this here as differential dissipation inequality DDI, then the DDI in this case would read the V dot of x would be, what would this be if I differentiate this over time? Differentiate this expression, so this quadratic storage function. Now, in specific case, q is still just an arbitrary q, but for our argument, right now it's not very necessary. So, what would happen if I look at the time derivative of this storage, this quadratic storage function? What would it be? What's the v dot? The v dot, I mean d dt v, right? That's what I mean. What's that? If it is quadratic. What happens if we differentiate?
We just get q times x.
Q times x, if we basically take the symmetry into account, yes, we'll do that. I'll go step by step. You could have said, I have to differentiate basically. So there's two time dependent quantities here, the x transpose and the x. You are correct, and this will be the result. I can differentiate each one, right? And I have a product rule. Q x dot. Okay? And then, now if I plug in, what do we get? For the x dot transpose, what do we get there? So for this term, I plug in this here. If I transpose this, I basically transpose the full equation, and I get here. I basically shape this in the middle, the other part in green. So what do I get for the transposed time derivative of the state? Plug it in. X transpose A, yes, plus U transpose U is a scalar in our case, so U was basically I can read that times B transpose, okay? That would be the yellow part. Right, this is the X transpose times the Q x plus 1/2 x transpose q, and now I have the x dot, which is just the kx plus b times u, is the green part. And now I can collect that. So what we basically get is so I have x transpose x transpose x, and I have some term which is basically a u x or x transpose u, but in general this would be what we get. So we have a 1/2 x transpose. I have an a times q plus, sorry, there's a transpose, a transpose q plus a q times a x. And here I have a b transpose x, b transpose a row vector times x, so this is a scalar quantity, right? This is a scalar quantity. Here I have an x transpose qb, x transpose row, q times b is still a column. So these are scalar quantities, therefore I can merge them. Okay? So this 1/2 in blue and the other 1/2 in blue, they become the same thing. So I basically get plus a, if you want, we say that this is a, so just check, we said that this is y transpose v, so then I say that this is a x transpose q b v. So shape this again, so this would be the blue part now, and this would be the red part. There in the red part I have something from yellow and something from green, and as mentioned, the blue part coalesces basically because these are scalar quantities. If it is expressed in terms of MIMO systems, then I can still merge it because of identity. I still get the scalar. Now, in this differential dissipation, inequality should be less than y transpose times u, which basically is x transpose times c times u, right? And thus, this would yield an ATQ plus QA less or equal than 0. Okay, that's first condition. And the second condition, Q times B equals C. Okay. And if you compare this to the Lyapunov stability theory, if you remember, what did we get there for asymptotic stability? We got a similar expression here because we took again a quadratic Lyapunov function as an example, and we also got a Lyapunov equation which basically reads a to q plus qa equals some negative p or whatever. So instead of having the inequality here, we need strict. Less or equal, we need strict inequality for, so less for the case of asymptotic Lyapunov stability. Right? That was the condition for Lyapunov stability. Here we have just stability, okay, because we have the equality sign here, but there are tools in order to prove asymptotic stability, even if that is satisfied with equality. Okay, so these would be equivalent characteristics in terms of the matrices A, B, C, and whatever the storage function looks like, the Q that we get there, to check passivity, derived from the differential dissipation inequality. So this would be in the nonlinear case, as we said, that would be the dx transpose f of x less or equal to 0 into g. The dv dx transpose g of x equals the h of x, or in the linear case, it would be the dA transpose Q plus QA less or equal to 0, and Q times B equals C. Okay, so that would be the nonlinear linear case, so-called harmonic conditions that we have. Now, of course, here the maybe art is like for finding the optimal functions. The art here would be to find storage functions. And in fact, we can say a lot more about storage functions. Here, we can find a whole set of storage functions, okay, for given systems. And we can identify two specific forms of storage, which basically are, if you want, the limits, the boundaries of this set. And one is called the available storage, the other one is called the required supply. Again, this has an intuitive value. The available storage is basically energy that I can, so let's say the minimum energy that I can extract from the system, right, within a certain time, providing some input-output condition. And the required supply is the energy that I need in order, the minimum energy that I need at least as much energy to drive it from point A to point B, so from an initial state to a terminal state. Okay, so these would be two different basically limits of our energy. I can formulate that in the following way. So this available storage, this would be the supremum over all inputs U for a given time t of the basically supplied power dt, and I take the minus here in order to basically symbolize this is what I can extract, and that's the maximum that I can extract by a suitable choice of u and y, or particularly y, the output. Okay. This itself is a storage function, and this would be the lower bound, and the required supply I call this Vr of x. This would be the infimum, which I can extract, basically which I have to provide in order to drive the system. Okay? So this would be what can I at least extract from the system starting at x0 in the interval 0t, and this would be how much energy, I put this in inverted commas because this is an energy interpretation again. If this is not directly energy related, it will still have the analogon. How much energy do I need to drive the system from x0 to x of t? How much do I need? And then we basically have a set of storage functions of which the available storage is the minimum, or the infimum if you want, the A of x, the infimum, and the required supply is the maximum. Okay, so this one would be what you can do at most. The other thing is the maximum here. And there are many, many possibilities in between. Okay, so these storage functions form a set. And again, this has a physical interpretation. Now, how is this now related, if you want, with stability? We can have a look at this. If there are questions, then of course you always please ask questions. Of course, we can take the storage function as a candidate variable function. Okay, it satisfies similar properties because it is positive definite. And if we now check for negative definiteness, we have seen that in the version here, basically this expression here, or this matrix inequality here, this would be the stability condition, and you can extend that to asymptotic stability. If you can show that this V dot is less than 0, then we have asymptotic stability. For the general case, we get stability, and then we can use additional on top versions of the Archimedes theory, which, if we only are in this case, we can still derive asymptotic stability. So there's, for example, one theorem, this is Lassalle's theorem. If basically we have to check for this case, this is basically the equality case, so which solutions are in there that satisfy this with equality, and if these solutions are just a single point of the equilibrium, then we have asymptotic stability, and often this can be done directly, just in one version. Let's do that for the system that we discussed in the beginning, the RLC circuit. In that case, the Hamiltonian, we have used that before, can be cast as a quadratic function with the charge and the flux. How I arrange them doesn't matter. I think I did it in the equations like this. Phi L U C. So this quadratic function can be cast as a 1 over L, 0, 1 over C. Can be cast as, in this case, as a quadratic function. 1/2 x transpose qx, right? This is quadratic, and you can see that the q, so this will basically take the role of my x transpose x, and this would be the q, which is positive definite, and which is also symmetric in this case. So here, this of course holds. And if you use it in the Port-Hamiltonian sense, we will always get that, right? We will, in terms of our stored quantities, we will always get something of this form, which is positive definite and symmetric. Now, if we take that as our storage function, so set V of x equal to h of qc phi l. Then, what is V dot? V dot of x, in this case, would be as we've seen, this would be a maybe I use a shortcut here. And basically differentiate this immediately. What I would say here is V dot. So this would be the h dot of qc by L. So this would be, if I differentiated qc, 2qc by 2c, so this would be a qc times qc over c, which is basically the e c times qc dot plus the I L times phi L dot. Okay, so I've done a direct differentiation of this expression. I differentiate this by QC, I get 2QC by 2C is QC over C is EC times QC dot and the second there. And if I now plug in what QC dot was, just briefly go back. So what, actually here's the link. So what we did here, so I plug in, okay, this is the phi dot equation, this is the QC dot equation, I plug in these two equations, okay? That's what I do. So for the QC dot, I think I already explained, for the QC dot, I get a minus EL minus EC over R1 plus the input, which is in our case the current, plus IL and phi L dot, we basically get a minus R2 EL plus EC. So just to show where this comes from, this is the QC dot. This is phi L dot. Now if you look at this, what you can see is, so this is basically, this is the, some always used EC, but here I've used, this is EL, okay, so this is EL, and therefore this and this cancels, right? This is one with a positive sign, one with a negative sign, and what remains is basically a product of EC squared and EL squared. So in our case, what remains is a minus EC squared R1 minus EL squared R2. And how could I cast that? Well, I could say that this is a EC EL, EC EL minus 1 over R1 and 0, 0 minus R2. Or if I want to cast this in the original X, then we could say that this is a, okay, this is the wrong way, but anyway, phi L QC, phi L QC, and then this would be a minus R2 over, this is basically an L times EL, so I have to divide by L squared, and here I have a minus 1 over R1 C squared, right? And now what can we argue here? What can we reason here? This is, what is this expression? Negative definite or negative semi-definite? Negative definite, why? So this is now negative definite, yes, exactly, why? Right, if we have these resistors, then this thing will always, I mean, this is not zero if the R2 is there, this is not zero if the R1 is there, and they are built into the circuit, so they are there, and therefore this has two eigenvalues, namely, what are the eigenvalues of this matrix? This is again a quadratic form, this is basically an xt, px, where p is this matrix in the middle, right? This would be xt p x, and p is, in this case, negative definite. It's also symmetric, and it has eigenvalues. Here are the eigenvalues. This and this, right? So these two negative quantities. For any, whatever the resistor, capacitor, and inductor are, this will always be asymptotically stable. So therefore, asymptotically stable and passive. Okay? That's what we get as an example. We've taken the Hamiltonian as a candidate Lyapunov function. We can prove directly here that this is asymptotically stable, and it is also passive, because in effect I've not yet shown that this is less than 0, but this is also I've forgotten something, so I didn't mention that. I've forgotten this guy here, right? I've forgotten the plus EC times I. So basically plus EC times I plus EC times I plus EC times I. So it is passive because this is, of course, let's first do this, okay? This is less, strictly less than this is u, and this is y. So in this case, it's a scalar product. It's strictly less because this part here, this is less than 0. So let's put it like this. Less than 0. Okay? We have an open system, so the input-output, the power supply, this is basically the power supply. I was my input, EC is the output. And since this is negative definite, as a quadratic expression, so what I get as V dot is less than y times u, in this case strictly less than y times u, therefore it is, if you want, strictly passive, and that's also asymptotically stable. Okay?
Is the passivity dependent on the stability of the system?
So passivity follows from this being less or equal than y times 0. Okay. So for stability, I would not be interested in the input output here. So this would be gone. I would not have considered the ECY. But what I obtain there for the Lyapunov, same Lyapunov function is something which is negative definite. That's why it is asymptotically stable. Okay. But if, of course, it's also passive because we've chosen. According to the Hamiltonian framework, always a passive product. I mentioned that immediately again. But so they are in principle different things, but they are related. Okay?
So you could have a system that's asymptotically stable and not passive then, could you?
Asymptotically stable, but not passive. So
Like that wouldn't make any sense, right?
sorry.
Like that wouldn't make any sense if you have, like, do we always have to be under saying, like,
So the thing is, what the system, if the system is passive, it is also at least stable. It need not be asymptotically stable. Okay, that's what we get. For asymptotic stability, we need a little bit more. Okay, and vice versa. If the system is asymptotically stable, it also has to be passive because this would mean it cannot generate energy. This would be a result of this just blow up. Okay. In fact, for we put this in here. Now for Port Hamiltonian, this is now here. Okay. For linear Port Hamiltonian systems, then we have x dot equals j minus r h dx plus g times u, and y equals G transpose dH dx with or in storage function and Hamiltonian h of x as storage function, v of x, we would have v dot of x equals h dot of x would be the dH dx transposed times x dot would be the dH dx transposed times j minus r dH dx plus a dHt dx g times u. This would always be passive since what is dHt dx j dH dx? Remember, J is, you remember what's the property of J? It's the power routing matrix, if you want. And it was geosymmetric. And then? What's dH dx transpose times J times dx? dH dx. So if I take the transpose of this is still, right? This is a scalar. So if I transpose it, it's this, and it's still a scalar. Okay? Thus, if my pt is minus p, then basically from here it follows. If this is the case, if this is a minus p, screw symmetric, then basically it means xt dx plus xt minus p x. This is 0, right? So they both basically add up to 0, and therefore this. So it is 0, right? If p is screw symmetric, because this here, this is this. This would be minus xtpx. So if a scalar product with a minus here is the same thing as the thing without the minus, it has to be 0. So this part disappears. So I basically just get a minus dH dx transpose r dH dx plus a dH transpose dxt g times u. Okay, because of skew symmetry, this disappears. This is the property of skew symmetry. If I have a quadratic form with a skew symmetric matrix, this is always 0, because the transpose is the negative. Now only the distributive part remains, and it's also a quadratic form with this r. R need not be positive definite, but it could be positive semi-definite. So therefore, this here is less or equal than 0. In our example here, it was the example. In our case, this is less than 0, but in general, it only is positive, positive semi-definite. And this here is, if you check, this is nothing but y transpose, right? So this is less or equal than y transpose, and The lesser or equal just comes from R being only positive semi-infinite. Okay? This here is positive semi-infinite. Okay, so in general, so passivity is always ensured due to the input output. I call it choice, but it is basically the setting. Okay, so since this is the transpose of this, we have ensured passivity always. As mentioned, not necessarily asymptotic stability, but certainly stability because of this less or equal than zero, so that's the case. If, like in our case, this is strictly negative, then we have also asymptotic stability, but that is not ensured. Okay? Okay, the last thing, I'm probably not gonna prove this, but that's something you just plug it in. I'll probably add this here as the last aspect, and then I think we'll finish this topic. I call this the compositional property of passivity, and that's compositional property of passivity. And that's now the interesting feature if we interconnect systems. Basically, if I close the loop of a passive plant, which if it is Poynhamiltonian, and we have seen that our standard physical systems will always be, can be cast in style. Well, depending on the choice of inputs and outputs that we've made. And we connect this with a passive controller, then the overall closed loop will be passive again and thus at least stable. We have to make sure that it is asymptotically stable, but this is that is something that is achieved. So I write this in words, the standard negative feedback interconnection of two passive systems is again passive. And let me just draw the diagram. So if I have, I call this a sigma plant, okay, with an output y1 and an input y1. And now I have a sigma controller with an input u2 and an output y2. And I close that with a standard feedback so that I have some v1, and this goes in here the negative feedback, and here I have some v2, and this goes in positively, so that would be the standard feedback interconnection of a plant with a controller. This could be, for example, some measurement noise or whatever we model there. This is our reference signal. Then this is again passive. Okay, I'm not going to prove this, but this setup, so if I consider this, so this would be the, basically, I should draw this a little bit longer, so the closed loop, this is passive again. Okay, sigma plant. I take this symbol, this would be the negative feedback interconnection as a symbol. Okay. Sigma controller. This would be passive again. If you compare it for the inputs V1, V2 and the outputs Y1, Y2, I also draw this one larger. Okay? can be shown without any problem. And that is now a nice result because this is exactly what is one of our standard control problems. Right? And more results of this type can be described or can be found here. Okay. So the last property that we've discussed now, passivity, has a very strong energy interpretation. Basically says, or it's mathematically defined as the property that a system cannot generate energy in itself. It can only basically get, or its energy storage will, at a future time, will always be less or equal than what it had at the initial time, plus minus the net energy supply. This bit can be cast in a differential version. That's what we showed here for the nonlinear case and for the linear case. We derived it here. These conditions show us the relation with Lyapunov stability theory because we have here this matrix inequality. It also appears in the Lyapunov case, but strictly lesser in that case for asymptotic stability. And we can see that any port-Hamiltonian system, again this holds for the nonlinear case as well, is always passive by construction, we've shown it here. And moreover, if I interconnect a passive system with a passive system by standard negative feedback, then I get again a passive closed loop. So for control purposes, this is something important. It can be used for controller design as well. So a stabilizing controller as a passivity property is also possible, and this is the whole theory of passivity-based control. After the break, we will look at the compensator scheme and then start with particular questions. What do we do about references, both set points and reference tracking? And if time permits, we will start with the optimal control part, otherwise this will be, I guess, in 2 weeks or so. But let's first have a 10-minute break and restart at 5 to 6, okay? 5 to 4.